So let's talk about dimensionality reduction, and this basically, like many times, just does the stuff that was in the book. They didn't do these calculations in the book, but I thought they were interesting enough to do. So if I make a new notebook, all right, and what's going on here is I have a variety of dimensions, and for each one, I'm just going to count how many points are on the edge. And you do that by just taking random numbers and seeing if they're less than 0.01. So that'll be on the edge. If any of them is there, then it's on the edge. And by the way, it occurs to me I'm underestimating the ones on the edge because I forgot to include the ones that were greater than 0.99 here. So I'm really only getting half the ones on the edge in each dimension. But anyway, it gets the main point here, which is you run this, and it's just a Monte Carlo simulation where you choose 1,000 points and see how many of those 1,000 are on the edge. And as you saw before, once you get up to 1,000 dimensions, they're all on the edge. So that's all that shows. And there's a flag defined there by modifying it. And here's the same thing that does the distance between points. So I'll just erase that old one and put this one on top of it. All right, and this does the same thing for a variety of dimensions. By the way, I learned from looking at these Python things, a trick in Python I didn't know about. In modern versions of Python 3, let you add an underscore into numbers to separate the thousands, so you can more easily read big numbers like 1,000,000, which is cool. So this will go up to 1,000,000 dimensions, and it's going to have two random points. Random minus another random squared. So it's going to add up the square of all those distances, which is what you do. It's a squared plus b squared and so on in many dimensions. And then you take the square root of that sum, and that's the linear diagonal distance between 2 points in the dimensions. It's just going to print out the total distance and then divide by 100 because you did it for 100 points. So it's going to have the average total distance between two random points, averaged over 100 points in each of those dimensions. And so it starts to take a while to calculate it, because here you've got to do 100,000 dimensions, and you have to do it 100 times. So as you can see, it's growing. The more dimensions, the further apart the points are. So that makes the point that your samples are sparse in high dimensional spaces, so you can't possibly get any work done in a high dimensional space like 100,000 or 10,000. You're going to have to lower those dimensions for your samples to actually trace anything meaningful out. All right. And then there's principal component analysis. So here we bring in the MNIST images, which we've used before. And I guess again I'll delete this old stuff. We don't need it. This is just going to fetch them from an online source. It's in the OpenML library. These are the same handwritten digits we've used before. And now we're going to choose the right number of dimensions. So it's still running, it's fetching. This is the one that has, I think, 70,000 images. So it's going to take the first 60,000 of them as training data, and then remaining 10,000 as test data. There we go. So there's the first 16 images, 4x4. So now we're going to find out how many dimensions it takes, which does PCA, Principal Component Analysis Reduction. And I want to go down to where it captures 95% of the variance and just see how many dimensions that'll take. All right, the answer is 154 of this 730 something dimensions are needed. All right, and so now we are going to do a model with a random forest. So this is going to use a randomized search to find a combination of hyperparameters for both the principal component analysis and the random forest classifier using only two dimensions: the number of components you keep of the principal component analysis and the number of estimators, which is the number of random trees you're going to mix together. Those are the only two things. So we're only going to use 100 training images and 10 iterations to make it faster. So let's take a look at this code. All right, so here it is, importing the randomized classifier, random forest classifier, and random search. And then we're just going to make a pipeline of principal component analysis with the random forest classifier. And so it's going to do a search for those two parameters and fit them. And oh, it looks to me like I trained it on 1,000 images here, not 100. But I think it'll work. I just tried to choose it to see how slow this is. The only reason to train it on less is to make it faster. And let's see how slow it is. Here it is all the way down to here. Now it's doing the fit. This green arrow tells you which step it's on. So let's see if this takes forever. I'm thinking it won't. It's 11:56. I'll give it till 11:58, and if it hasn't moved, I'll stop it and run it at 100. Oh, there we are. Didn't take very long at all. So it shows 465 estimators, 465 trees, and only 23 parameters. So remember, it took something like 150 parameters to capture 95% of the variance, but here it decided you really only need 23 of the components to get the job done, and 465 estimators, and then you will have 85% success at classifying those them into the 10 groups. So that's interesting, perhaps not surprising. You really don't need very good representation of those digits to tell the digits apart. It's okay to capture less than 95%, substantially less. And so now we're going to see, going down to 23 dimensions, how much have you messed up the images? That was what occurred to me. That seems like you must have messed them up pretty badly, and we can find out. This will compress it down to 23 parameters, and then reconstruct it and print up the reconstructed images from 23 parameters. So there we are. The original is 784 dimensions, and the one with only 23 dimensions. And as you can see, it has pretty well distorted them, adding some extra loops here. In fact, it would seem to me like this 2 might get confused for an 8 now, when that wouldn't happen in the original. But anyway, this turns out to be relatively successful and much smaller. And that's it. There's some various flags to find from varying these, but that's where you get to see these dimension reduction operations in practice.